Hello guys, in the last class we have concluding our session with introducing a fundamental matrices, and where we completed the discussion of the solution for the system of linear equation which was homogeneous. And we supposed to tell that in the today's class we will start with the non-homogeneous linear system, but we decide to first go to the stability part, stability of a linear system, then we go to the non-homogeneous linear system part. Okay, so first we will discuss about the stability of the linear system. Of a okay, let's say dx dt equals to a1x plus b1y and dy dt equals to a2x plus b2y. Okay, now our auxiliary equation is, that is the characteristic equation also. So our characteristic equation is, let's say, lambda square minus a1 plus b2 into lambda plus a1 b2 minus a2 b1 equals to 0. Okay, let's say two roots are, let's say two roots are lambda 1 and lambda 2. Okay, now if the roots are real, distinct and the same sign, then 0 0 is a node. If the roots are real, distinct and the same sign, then 0 0 is a node. Okay, if the roots are real, distinct but the opposite sign, then 0 0 is a saddle point. If the roots are real, distinct but opposite sign, then 0 0 is a saddle point. Say saddle point. Okay, third, if the roots are complex conjugate, if the roots are complex conjugate, but not merely purely imaginary, but not completely purely imaginary, then 0 0 is a spiral. Four is, if the roots are real and equal, then 0 0 is also a node. If the roots are real and equal, then 0 0 is a node. If the roots are purely imaginary, then 0 0 is a center. If the roots are purely imaginary, then 0 0 is a center. Say center. Okay, and finally the critical point 0 0 of a system is stable. The critical point 0 0 of a system of the system 1 is stable if both the roots have non-positive real parts. And is called asymptotically stable. Asymptotically stable if both have negative real parts. Negative real parts. Okay, so this is all about the stability of the linear system. Okay, now this is the system 1. Okay, now this is a very important concept in the for the linear system, and you can expect the sometime the question of in some competitive exam like NET and GATE, you can get some question from the stability of the linear system. So you should remember all this point I mentioned here. So if you remember all this point, then you can easily find out whether the 0 0 is a node or a saddle point or spiral center, and when it is stable or asymptotically stable. Sometimes you find this question in the competitive exam like NET and GATE. Okay, so we will give some example, and from there we can find out whether the critical point is our node or saddle point or whatever it is. Okay, so let's take an example. Let's take the example of so consider this system dx dt equals to 6x minus 3y and dy dt equals to 2x plus y. Okay, so in this situation our characteristics equation will be, so characteristic equation is lambda square minus 7 lambda plus 12 equals to 0, and which implies that lambda 1 equals to 3 and lambda 2 equals to 4. So here we get the roots are real, distinct and the same sign. So we get the roots are real, distinct and the same sign. So here 0 0 is a node, right? Now take the another example. Dx dt equals to 4x minus y and dy dt equals to x plus 2y. Okay, so characteristics equation is the characteristics equation is lambda minus 3 whole square equals to 0. Okay, so our lambda 1 lambda 2 both are 3. Okay, so what we get, the roots are real and equal. Okay, so we get the roots are real and equal. Okay, so then 0 0 is a node. Okay, now consider the another example. Now this is dx dt equals to 3x plus 2y. Okay, and dy dt equals to minus 5x plus y. Okay, now first we find the characteristics equation of it. The characteristics equation is lambda square minus 4 lambda plus 13 equals to 0. Okay, so which implies that lambda equals to our 2 plus 3i and lambda 2 minus 3i. Okay, so here the roots are complex conjugate. So here the roots are complex conjugate, right? But this is not completely imaginary. Okay, so since the roots are complex conjugate, but not purely imaginary, so 0 0 is a spiral. Okay, let's take the another example. dx dt equals to x plus y and dy dt equals to 4x plus y. So our characteristics equation is lambda square minus 2 lambda minus 3 equals to 0, square minus 2 lambda minus 3 equals to 0, which implies that lambda 1 equals to 3 and lambda 2 equals to minus 1. Okay, so here the roots are real distinct but the opposite sign, so 0 0 is a saddle point. Since the roots are real distinct but the opposite sign so 0 0 is a saddle point. Okay, so this is all about the stability of a linear system. Now we start the solution for our non-homogeneous case. Okay, so now we discuss about the non-homogeneous linear system. Okay, so we consider here the system, let's say x dash equals to p of t into x plus gt. Okay, let's say this is our 1 where pt is the our n cross n matrices and gt is our n cross 1 vector. Where pt is the n cross n matrix and gt is n cross 1 vector, mainly column vector. Okay, so the general solution of one will look similar to we discussed in the last section. Okay, so the general solution of one can be expressed as x equals to c1 x1 t plus c2 x2 t plus so on cn xn t plus some vt. Okay, let's say this is our 2. Okay, now here this part is our general solution. So where c1 x1 t plus cn xn t is the general solution of the homogeneous system, is the general solution of the homogeneous system, right? And in case the homogeneous system is x dash equals to pt into x. Okay, and vt is a particular solution of the non-homogeneous system 1. Say particular solution of the non-homogeneous system system 1. Okay, now there are several ways to find out our particular solution. Mainly we discuss here the diagonalization process, how we can use our diagonal matrix. This is our matrix pt. We will turn this matrix to a diagonal matrix, and from there we try to find out this vt. Okay, so we use the process of diagonalization. Okay, okay, so we begin with the system x dash equals to ax plus g of t. Okay, where A is a n cross n diagonalizable constant matrix, where A is an n cross n diagonalizable constant matrix. Okay. Okay. Now let T be the matrix whose columns are eigenvector of A. Let T be the matrix whose columns are eigenvectors let's say xi1 and so xi(n) of A, and we define a new dependent variable y and define a new dependent variable y by x equals to ty. Okay. Now this is our 3 and this is 4. Okay. Now we substitute for x in 3. So we substitute 4 in 3 and we get t of y dashed equals to a of ty plus g of t. Okay. So by multiplying t inverse, it follows that by multiplying t inverse, it follows y dash equals to t inverse a t y plus t inverse z of t. Okay. Now we call this is as dy plus ht, and this is our 5, where ht equals to t inverse gt, and where D is the diagonal matrix and D is the diagonal matrix whose diagonal entries are the eigenvalues let's say lambda 1 to lambda n of A. Okay. Now equation 5 is a system of n uncoupled equation for y1 to yt. As a consequence, the equation can be solved separately. Okay. Now equation 5 is a system of n uncoupled equation for y1 to ynt, for y1t up to ynt. Okay, so the equation can be solved separately. So the equation can be solved separately. Okay, so if we try to solve it separately, then we something get. So equation 5 has the form yj dash t equals to rj yj t plus hjt, where j equals to 1 up to n. Let's say this is 6. Okay, where hjt is the certain linear combination of g1 up to gnt. Where hjt is a certain linear combination of g1t up to gnt. Okay, now equation 6 is a first order linear equation, so it can be solved. So by solving 6 we get yjt equals to e to the power rj into t, t0 to t, e to the power minus rj s and hj s ds plus cj e to the power rjt. Okay, where j equals to 1 to n, and this is 7. Okay, so where cj are the arbitrary constant, where cj are the arbitrary constants. Okay, and finally the solution x of the equation 3 is obtained from equation 4, and finally the solution x of equation 3 is obtained from equation 4. Okay, So this is how we can derive a solution for non-homogeneous linear system. Okay, now you should notice one thing, that when we multiply by the transformation matrix T the second term on the right hand side of the equation 7, that is this term produce a general solution of our homogeneous equation x dash equals to ax, while the first term it will yields a particular solution of the non-homogeneous system 3. Okay, so when multiplied by the transformation matrix T, when multiplied by the transformation matrix T, the second term on the right side of equation 7, second term on the right side of equation 7 produces the general solution of the homogeneous equation x dashed equals to ax, while the first term on the right side of equation 7 gives a particular solution of the non-homogeneous system. The non-homogeneous system. Okay, now let's take an example of this. Okay, find the general solution of the system x dash equals to -2 1 minus 2 x plus 2 e to the power minus t plus 3t. Okay, so let's say this is our matrix A and this is our G, so ax plus gt. Okay, let's say this is our 1. Okay, so now first we find the characteristics equation of it. Okay, so solving the characteristics equation, we get the roots r1 equals to -3 and r2 equals to minus 1. Okay, and the corresponding eigenvectors are corresponding eigenvector are xi1 equals to 1 minus 1 and xi2 equals to 1 1. Okay, so this is 2. So the general solution of the homogeneous system is, so the general solution of the homogeneous system is x equals to c1 1 minus 1 e to the power minus 3t plus c2 1 1 e to the power minus t. Okay, let's say this is our 3. Okay, so now we'll write the matrix T. So T will be our 1 by root 2, 1 minus 1 and 1 1. So this 1 by root 2 come from the normalizing the eigenvector. We have normal this eigenvector. Okay, so that's why this 1 by root 2 is in. Okay, and the T inverse will be our 1 by root 2, 1 minus 1 1 1. Okay, now let's say this is 4. Okay, now let x equals to ty and substitute in 8. Now let x equals to ty and substitute this in 1. Okay, so we obtain y dash equals to diagonal matrix D of y plus T inverse G of T. Okay, and this will be our minus 3 0 0 minus 1 into y plus 1 by root 2 2 e power minus t minus 3t and 2 e power minus t plus 3t. Okay, this is 5. So if we simplify this, we will get y1 dashed plus 3y1 equals to root over 2 e power minus t minus 3 by root 2 t and y2 dashed plus y2 equals to root over 2 e power minus t plus 3 by root 2 into t, and this is 6. Okay, so each of the equation is first order linear equation. So we get y1 equals to root over 2 by 2 e power minus t minus 3 by root 2 t by 3 minus 1 by 9 plus c1 e to the power minus 3t. Okay, and similarly you get the y2 also. Okay, so I just keep it blanks. Okay, so our solution will be x equals to t of y. Okay, and that equals to will be 1 by root 2 y1 plus y2 and minus y1 plus y2. Okay, now we put the value of this and we get the our solution. Okay, so this is how we can derive the solution of our non-homogeneous linear system. Okay, so that's all for the today's class. Thank you.